Hello and welcome to lesson 33. So today we're going to start looking at uniform acceleration questions, and we're going to be doing it first with VT graphs. And I'm also going to be dividing this single topic into several lessons. So a while back when I first started teaching, I tried to do what people typically do. Hey, we're doing uniform acceleration equations today. And then basically you spend the next 4 or 5 days trying to fix all of the chaos and confusion that results. So I've developed a way to separate this out into sort of doable bite-sized pieces, you can call it. So they're going to be type 1, type 2, type 3. And by the end of it, I've had students start to say, well, there's really not any difference between these types. And I point and say, I agree, and say exactly. That means you understand it now. But there's slightly different scenarios that have to be dealt with, slightly different ways, and it's just too much all at once. And so I hope this works for you. Okay. Before we get into the uniform acceleration equations, we're just going to remind you about the dt, vt, at, so position time, velocity time, acceleration time graphs, and the information that's on each. So if we have a position time graph like that, then it's possible. For this course, we're talking about uniform acceleration primarily, right? So if it's uniform acceleration, one of the possible results we've mentioned was that it's a nice straight line, right? So I could even make that red to go along with that idea that it's uniform. We talked lots in the past about how it could be increasing its velocity more and more, or it could be increasing its velocity, but not as quickly or not as much as time goes on. Okay, so there's other possible types of motion. But this is the one we're studying primarily in this course. And then at that point, if you look at the slope, so this, I could even show you here the idea of like slope here, slope there, slope there. So this number, this number, this number would be on here, like dots on here, right? So the idea that slope on a position time graph gives you the velocity. So that's what this is saying. I didn't even show it that time, so I'll show it better this time. So, slopes to make this thing anyways. And then, in this case, with the velocity time graph, when we look at the slope here now, so let's do this slope, and we see that would give us acceleration, right? And so we end up with the acceleration value on this. So if I wanted to, again, color code things nicely, I could select tools not working here for some reason. Just give me a minute. There we go. That could be purple to sort of match the idea there. Okay. So if you're looking here, from this one, you can get like slopes give you velocity. I should add that in. Slope for velocity. And this one, you have the acceleration value, but you can't really get displacement. And you'll see here that we're going to be able to get displacement from VT graphs. You have velocity directly reading from it. I should add in more information here as well. On the dt graph, of course, you can get d, d directly. Slope for velocity, but you can't get acceleration. On a VT graph, you can get v directly, times directly, acceleration gets slope, and then we're going to see this part here soon, okay, that we can get the area under the graph. Okay, so that's, we're going to be doing this very soon, and I can even mention here why that is, right? So if you look here, we got this area, let's say, think of the area formula for this. Area equals 1/2 base times height, right? Literally just a triangle. And so you have 1/2 of a base, which is a time, so in seconds, right? So time, and then the vertical is delta V. So if you think about what you have there, you have units anyways of seconds times meters per second. I'm just trying to move that up so I have room to show everything I want to show here. Second. There we go. Cooperating, but it was. So if we look at the units here, this is seconds, and then this is meters per second. You can see that we're going to get meters here, right? So this is the displacement, right? So it's just a way of calculating the displacement. If you think of an easier example of this, a simpler example of this idea would be if you looked at, you're just traveling at a constant velocity and times your time, right? Then, if you look at your velocity formula, velocity was distance over time or displacement over time. So then displacement, of course, would become velocity times time. Like that's the area. That's your length times width. It's area. Okay, so I'm just spending a little more time there just to make sure it's clear, why that is, and we're going to be doing that a lot. Okay, soon, not yet, but so a little preview of it. You don't have to totally get it at this point. You'll see more of it soon. From the acceleration time graph, it's really hard to get positions. Even velocities, like it's everything's kind of hidden in that one. So the big green circled one in the middle is really handy, and that's why we've already started doing VT graphs in the previous lesson. Okay. So if we look at an example here, I just clone this page and go through it with you bit by bit here. Okay, so let's just grab, let's just do this. Okay, so if you were given in type 1, you're going to be given V1, V2, so initial velocity, final velocity, the amount of time it took, and so we're going to calculate, the acceleration and the displacement. So what's going to, doing this should be pretty easy where you just go, okay, well, V1 was 5. Now this is just a VT graph, doesn't have to be drawn to scale, just representing that we're increasing from 5 to 20, relatively speaking. If you wanted to try and make it, more realistic, that's fine, but no one cares, it doesn't matter. So we're going to start at this velocity, we're going to end up at that velocity, and then you have to recognize that it's going to be a nice straight line because we're talking about uniform acceleration, right? So in this question, this is just the given information shown, but part of the wording for this one would have been, an object. Let's write out what the question would have been. In a car, let's say, accelerates from an initial uniformly. Here we go. Uniformly accelerates from an initial velocity of 5 meters per second to a final velocity of 20 meters per second in 5 seconds. Be really common for it to be like 5.0 and so on and so on, but we're not to worry about significant digits every time, right? So just there's your information, right? So then the question would be, the task would be to determine, right, the acceleration and the displacement. All right, during the interval. Okay, so that's think of what the question would have been from that paragraph of words. You'd pull out the information and see, okay, well, we have the initial velocity, the final velocity, the time that took, and we're asking for the acceleration and displacement. So this is what I'm calling type 1 because it's one of the easiest types. Okay, so making the VT graph isn't hard. I'll finish the job here and put that 5-second mark on, and so on. So VT graph, I would think of that as like part A, VT graph. Please get used to that, okay? Because they're really handy to analyze things, help you understand what's really going on. And we're going to use them to help ourselves be able to calculate things for the first bit, for sure. So with what we're doing here, so this, if I'm going to go ahead and get the acceleration first, so let's do this. Acceleration equals, and we know it's delta v over delta t. And so in this case, we can jot it in as v2 minus v1 over, that's a weird one, right? v2 minus v1 over delta t. And so we can put it in as 20 take away 5 over 5, gives us 15 over 5, which is just 3. We have it's 3 meters per second squared, therefore blah, 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 right? Okay, so we've gone ahead and just calculated the acceleration. Now, I'm just going to point out that in terms of VT graph stuff, what we mentioned just on the previous slide was that we're talking about slope as a concept. We don't really need to think about that a ton, but it's nice to sort of see on here that this slope is that 3 meters per second squared, right? And quite literally on this diagram, you've got your 15 and your 5, right? But the slope can be shown anywhere as well. So it's kind of nice to sort of think of it both ways. Okay. So slope of VT graph, right? We're talking about, for acceleration. Okay. So that is the starting point for us here. So I kind of meaning to think of this as two different ways, right? Where by uniform acceleration equations, you're going to have this work from scratch as an equation, right? In using VT graphs, you're thinking of slope. Okay, so that's the that's sort of what I want you to just be aware of, so that you can use VT graphs nicely to help yourself through questions. But it really is the exact same work, right? So using uniform acceleration equations, well, yeah, this is an equation. It works. We don't have to talk about slope. Okay, so it's the same stuff either way. All right. Next step for us is to go and look at getting displacement. Okay, so this is the first time we're going to do this for real here. So we're going to, what do I have here? Yeah, the area stuff, right? So basically, we know this concept that I introduced, that area under a VT graph is the displacement, right? So I'm highly recommending you literally write it out like this, like delta D equals area. And even actually this line here, I really, really encourage you to do. Just really help it make it very obvious that you have this rectangle and you have a triangle. That's the area under that graph. Forget about the rectangle part. There's a rectangle area. So basically, if you were going 5 meters per second for a whole 5 seconds, this rectangle represents the area that you would have, the displacement. So I'll use actually a different one. I'll get rid of that one. This right here, this displacement right here, call that delta D, right? That displacement is like how far you'd go if you didn't speed up, right? And then this displacement is the extra displacement because you're going faster and faster, right? So this is displacement delta D due to the 5 meters per second that you for sure have the whole time because you started with it. And then this is the extra displacement, right? This one is the extra displacement because you're speeding up. Obviously, you're going to go farther, right? That says speeding up, sort of. Yeah, so that is what we're thinking of here. And so when we go to try and calculate this stuff, you can see you have like a length times width here of just 5 times 5 in this case, right? It's just the, quite literally, if you think of it in terms of the variables, which this will bring us, help us work towards the equation version of everything. But obviously this is a delta T and then a V, right? A V1 really, right? Delta T times V1. So delta T here and V1. Right, that's your area. And there's going to be an equation later on, you'll see, that's going to start out with V1 delta T, right? Or the other order. The other equation, the other part of this is the area. So 1/2 of base times height. So 1/2 of, and you can tell here that the variables are really, in this case, we have a V1 times a 15, a delta V. Right, that's not going to be the official form of the equation later on, but it builds it. So when we go to talk about the official uniform acceleration equations, we'll understand why they make sense, because we'll be able to see how they're built. Okay, for some of them at least. We don't bother necessarily for all of them, but nice to know what we're doing. Yeah, so we get numbers 25, 37.5. You add it up, you get 62.5. Good to go, right? That was pretty easy. You just get the area under the graph. Okay. So you travel 25 for sure, even if you didn't speed up, and then an extra 37.5 because you're speeding up. Grand total of 62.5 meters. Uniform acceleration equations, right? There are uniform acceleration equations that can be used for this. They aren't needed always, like we're able to do this without them, right? But of course, we're going to do those eventually because we want to be able to tackle things efficiently and whatnot. But we're trying to build understanding right now, and so we're just seeing what makes sense. Okay, so we are going to come back to that stuff. But for now, I need you. I'm insisting you need to do this. to help learn. Okay, I've tried a lot of things to help students learn this, and this is what I found works the best. Okay, so please follow along with that process. I don't want you just YouTubing and cutting to the chase of the equation results, because I'm going to have on assessments solve using VT graph method. Right? You need to do it. It's mandatory. So here we've got a so-called like slowing down case. So I have the little stories in there as well. So a car slows down uniformly for 2 seconds with from an initial velocity of 40 meters per second to a final velocity of 10 meters per second. Determine the rate of acceleration and displacement. A very similar question, right? We can draw the VT graph. Just obviously we're starting at 40 and we're ending at 10. So that's a pretty good scale there. 2 seconds is somewhere along there. So we're starting at 40 and we're ending at 10. And again, we're talking about uniform, right? Acceleration. And so we're talking about a nice straight line. I don't know if I ever said that on the other one, right? Nice straight line. But that's what I was getting at. I think I got distracted by many other things that I was trying to cover. But yeah, there's your VT graph. They shouldn't be a stressful thing. They're just a representation of the motion, and it builds on our previous work of understanding what that would mean, right? If you look at that VT graph, you should be able to tell me and illustrate what that would mean. You're running at 40 and then slowing to 10 or something like that, So you can't run at 40 meters per second, though, of course, that'd be over 100 kilometers an hour. So yeah, we're looking for acceleration and displacement. So just like we did on the previous slide, I'm just going to show it here, right? Acceleration, of course, you could look at the slope, or you could think of it as an equation, right? So the slope or the equation version. So this is the slope version, where it's like slope equals delta v over delta t, and delta v is that, and so on and so on. So you end up with an acceleration of negative 15 meters per second squared. And to relate to the recent direction of acceleration thing, you can see that it's in the opposite direction of the velocities, right? So I'm going to put V's are positive, acceleration is negative, and so it kind of confirms that it's a slowing down situation, which clearly it was in the question. And I guess we'd say like therefore the acceleration rate is negative 15 meters per second. What this is actually implied here is like forward, but we know that negative of forward means backwards, right? So it's accelerating backwards, slow, all those things. That's just the ways to think about this. So therefore the acceleration is, and so on, right? If we were doing this by the equation, then it would be the same stuff. It would just be acceleration equals delta v, and then delta over delta t, and same stuff. Okay, so equation method versus VT graph method for acceleration. There's really no difference. Where the issue or where the power of the VT graph method comes in, of course, is that we can just get displacement, right? Now, there's a bit of an issue here. So I'm focusing on it. Says here about the sign of delta v, right? Delta v, of course, is a negative. It's a negative 30, right? But in terms of displacement, right? This car is going forward, right? It's traveling forward a certain distance. So it's traveling forward. It would travel forward 80 if it didn't slow down, 40 times 2. But it's not going to travel quite as far because it's slowing down. Okay, we've got positive displacements. It's all positive forward stuff, right? The only thing that was backwards was acceleration causing it to slow down. It doesn't end up going in reverse. So if the displacements are positive, the area would have to be positive. And so the delta V in the area equation has to be a positive value. Literally look at as an area formula, and there's no negatives there. Everything's above 0, right? So area under the VT graph is a triangle and a rectangle and a triangle again, right? And then we're going to just put the same values in as normal. So we got your 20 and your 10 for the length and width. You've got 1/2 of the base. That's 2 still for the triangle, right? The 2 just transfers up. And then the delta V is a size of 30, essentially. We're not putting it in as a negative. It's a positive height or a positive displacement. To me, that's the only little downfall of the VT graph method, is that can be a stumbling point for people. But I don't think anybody's going to say, oh, it went 50 meters backwards while slowing down going forwards, right? So we end up with 50 meters. Therefore, so on and so on. Okay, so that's, yeah, a slowing down case of type 1, but still just a type 1 question where you're asked for the acceleration and the displacement. That's the key, right? What are you given? And then, so you're given, if you're given v1, v2, and delta t, it's a type 1. You're asked for acceleration and displacement. Soon it's going to be obvious when we get to the equations if there's 5 variables and you're given 3 and you're solving for 2. And so there's lots of different combinations of what you can be given. That's what I'm breaking into these types. All right. That one there. Yeah, let's look at this one. So this question here, initial velocity is negative 20. Final velocity is negative 4. And the time interval is 2. So it's a very similar question, just with opposite directions going on. And so a VT graph for this one can be done where you're saying, okay, we're starting at negative 40. We're going backwards really fast. And then we're slowing to backwards going 4. Okay, and that happened in 2 seconds. So we have initial velocity of 40, final velocity of 4. I'm just going to sneak my 4 down a little bit so it's not interfering with my 2, my label there. Okay, so slowing down uniformly. I didn't have the question written, but I think we're getting used to the idea that you would just pull that information out and work with it, right? So that's our situation there. So acceleration, of course, just equals delta v over delta t, and you can be mindful of the fact that it's rise over run, it's slope, right? So rise over run, I'll make that look like the word run. So you have here a rise and a run, right? So the concept is, the connection to the concept is clear. So delta v obviously equals, in this case, I missed my negative on there. The change from going from minus 40 to minus 4. So if we're doing this, really, really thoroughly, then you'd put that in as like literally a v2 minus a v1 over 2, since we can just throw the number in there. V2 is negative 4. V1 is, so we're taking away from that, V1, taking away a negative 40. So we're adding 40. So we have a negative 4 plus 40. And so obviously the number is 36 there. There's a couple ways you can do that. You could trust the plus minus button on your computer and avoid thinking. So negative 4 plus 40. It worries me when I see students do that because it makes me think they're not thinking. Instead, obviously, you could reverse the order of things and just say 40, take away 4, right? You have a 40 and a negative 4. Combine them. That just means to add them. So we get 36 over 2. And so we get 36 over 2 is 18, right? So 18 meters per second squared, right? Just a little sanity check here for me. So there we go. We have a positive number that we end up with here. And so we're getting that the acceleration is positive. Okay. Well, analyze here. We've got a positive acceleration, right? We have negative velocities, and combine that to a slowing down situation. That's what I'm just trying to review that previous thing that we just saw, right? And get you thinking about those things as we go through here, right? So that is obviously here, you can even see positive acceleration, positive slope, right? But you can see we're slowing down, right? So that's slowing down from fast reverse to slow reverse. So it's hopefully all starting to come together and jive and make sense, right? So we've got the acceleration, good to go. And then the displacement, just doing this one from scratch with you here. Displacement equals the area. Now, I'm going to put in quotes under. When I say under, people say under a graph, they actually mean between it and the 0 in the axis, right? So we're talking about, in this case, the rectangle, and I'll draw the triangle, the way it is on there. And that's what we're talking about. So length times width would be a 2 times a 4, and 1/2 of base. The base is a 2. The height we already know is a 36. I don't know. 36. Oof. Right now, The issue with negatives here is that if we want this to say a negative displacement, we really want that, then we have to consider the fact that this is a negative and that's a negative. And then we'll get our grand total of a negative displacement. Obviously, you could do this question without those green negatives, right? So you could just do half of 2 is 1, so we have 8 plus 36, or it could be 8 plus negative 36. Negative 8, sorry, plus negative 36. So you end up with, just the 36 and the 8 adding together, getting your 44. And so you're saying, okay, the answer is 44 meters. And, it was going backwards the whole time. So, of course, it's, a negative answer, right? Negative 44, i.e. 44 backwards. Right? So it's unfortunate that the reality is here that this would be actually have a forward there, negative 44 forward. In other words, 44 backwards. And we're just trying to be consistent about how we label things, and the negative in there makes it so that you kind of have to, if you're being thorough, show that. Again, though, I'd be totally okay with the green not happening at all, in which case you just know that it's backwards, right? So without the green stuff, it would have been the same work. It just would have been this, and you would have just said, hey, I know the answer is backwards. So this would have had to have been backwards directly, right? So this would have had to have been backwards because we know it's backwards, right? So either you know it's backwards or the math tells you it's backwards. So the math being the negatives. Undoing my changes there. All right. So that is that. Looks like I might have done a question wrong here. Something. What did I do wrong? 2 times 4 is the 8. 36 half of 2. Uh-oh. No. 24. 36. What was my 36 was wrong? Delta V. 36. Looks like I was wrong in the past. Oh, but it was 4 and 20. Ah. I'm sorry. I made a mistake here. I chose delta V from here. Oh, no, but it was a different question. So it was 4. I did it as 4 and 40. Okay, that's why. Okay, so it wasn't really a mistake. I just accidentally took this as 40. I apologize. Okay, so there's the one with it as a 40, and then we have a bonus question here worked out where it was a -4 and -20. Same stuff. I just misread the number. Okay, that would be a very, very well. That wouldn't even be a marked deduction really for you if you did that by accident. But if any, it'd be like minus a 0.5 out of like 10 marks or something, right? It's just a little oops. So there you go. Yeah, hopefully that's making sense for you. So in here, I'm just asking you to sketch position time and velocity time graphs for a motion. Obviously, the point is we're going to use those things, right? In this one here, down here 11, you're just going to draw the VT graph for now, and then look at why it would be difficult for you to answer this one fully, right? So that you'll notice it's not really a type 1 case anymore. It's a little different. So think about like, why is it a little more difficult? What is the step that you can't do? Start to get you thinking about what the next kind of questions are going to look like. But this question is just straightforward, where you're just going to get the given information, do a VT graph, get the acceleration and the slope, right? Or acceleration and the displacement. I added it on there. Same thing here, get the acceleration and the displacement. Right? I'm just modifying these questions to make them be everything we can do with this type, rather than the textbook questions not being as thorough. Same deal here. You can do that one fully. So that should be all good. This is your regular practice stuff. And then I have one that's not going to be submitted necessarily right away, but I'm going to make a 33 challenge question Dropbox. And so this situation is going to, stretch your limits a little bit in terms of thinking about directions and whatnot. So we have a boat that's going back, accelerating backwards, right? Once the boat reaches a velocity of 4 meters per second backwards, it's shifted into forward and starts force pushing forward. So it starts accelerating forwards, ends up later on traveling at 5 meters per second forward. Notice that in a boat, you're going backwards. Just because the gas gets on, the thrust gets on forward, you're still going backwards for a while, right? You're just slowing down as you go backwards. And so hopefully maybe you've been in a boat enough that you can picture what I'm talking about there. The textbook question was terrible. It was talking about a car. So this was originally in the textbook was a car going down a ramp, and when it when it ends up going 4 meters per second backwards, it gets shifted into drive. And I'm like, oh my gosh, you'd have to be like spinning your tires. Like it would work on a snowy ramp where you have enough traction to slow yourself down and then go forward, right? By spinning the tires. But that's about the only situation that would make sense. Otherwise, you're gonna destroy your transmission. That's not good. Yeah, so drawing a VT graph, labeling this thing and describing the sections of the movement, like the portions of the movement where you're speeding up or slowing down, and talk about acceleration signs and so on. This is very doable. You just have to work your way through it. Okay, so feel free to ask questions, though, of course, as you work through things. And that's it for this one. So that's your first kick at the can at uniform acceleration questions. And I'm not even showing you the uniform acceleration equations yet. So please don't look them up. Please don't start trying to use them yet. I'm going to help you with it as we go. All right. That's it for now. Talk to you later.